right, so bad news about basketball, but the good news is that there's more baseball. So, baseball game tonight. Watch. I guess you can't watch it. It's on like Big Ten Plus or something like that. So if anybody knows how to pirate that, let me know. Anyway, last time we were talking about stacks, and the implementation that we chose was to use a list, right? So here, let me go over to my stack here, and we've got an underlying list here, and we chose to make that into a linked list, right? And then again, we called that a thin wrapper because if you've got an underlying data structure here that you want to reuse its its functionality, you wrap it up in a thin wrapper called a stack in this case, and then you restrict access to it only through these operations, push and pop. That's what imposes a structure onto this data structure, right? Now I could have gone a different route. I could have said, well, I want I want to extend a linked list, right, of elements of type T. Now, that's another way of doing code reuse instead of using composition, but that would have locked it into a hierarchy. Remember that this has to follow an is-a relationship. Is a stack a linked list? Right. Well, what does a linked list do? It allows you arbitrary access to whatever you want. So we'll go ahead and push 10, 30, and 40. Oh, I forgot to put in 20 there. Stack dot insert or add a particular index here, say 2, and we'll put in 20 right there. I guess at 1. Does that sound like a stack to you, where you can just take an arbitrary dish and shove it in the center? Nope. So I do not want to lock this into an inheritance hierarchy because a stack is not a list, right? It doesn't follow that is-a relationship. It kind of violates the Liskov substitution principle in some sense, right? So instead of using an inheritance, right? Instead we used what was this called? Composition. Use composition. And this goes all the way back to our discussion on object-oriented programming, right? Object-oriented programming, inheritance is nice, but generally you should prefer composition over inheritance because of this. Or like the quintessential examples we gave were a person and a director and an actor, or a person and a writer, or something like that, right? A person can be multiple things. So instead of locking you into a hierarchy where everything always has to follow an is-a relationship, this makes it a little bit more flexible. Okay. There's also some secondary functionality that we could have added to it. For example, a method to determine the size, a method to determine if it's full or empty if we want a capacity, a method to peek at the top, right? This is very, very common. You want to return the element at the top, but you don't actually want to remove it. You just want to take a peek at what is there, right? Really quickly here, what would it look like? Instead of a pop method, we would have public t peek, right? And instead of removing the last, what would I do? I would just get last, and that's it, right? I wouldn't actually remove it. I would just, get the element and return it, okay? So really, really simple once you're using a thin wrapper here, okay? All right, what about their cousins or their sisters or whatever you want to call them, queues, right? A queue is not a LIFO data structure, right? A queue is a line. And with a line, you have the beginning of the line and you have the end of the line, or the front of the line, we should call it, right? So this is the front and this is the end, right? And this is the queue, right? And queue is the British English word for a line, right? And if you're going to get into a line, where do you go? You don't get to butt ahead in the front. Instead, you go to the end of the line, and this is called NQ, right? And who gets served next? Whoever's at the front of the line, and that gets DQ'd. So if I were to NQ, say 10, 20, and 30, that means that 10 gets put into the queue, right? Again, it's going into this end, and then it comes to the front of the line, then 20, and then 30. And then if I were to DQ them, what order would they come out in? 10, 20, and 30. right? The same order that they went in. For that reason, it's called a FIFO data structure, a first in, first out data structure, because it's a line. And we don't allow line jumpers. We don't allow people butting into the line or allowing somebody else to get into line, right? We always serve the person at the front of the line, the next person there. The two operations, again, are NQ and DQ. That's what I like to call them because it keeps it generic and general. Any implementation is going to have a different terminology for these things. Sometimes they call them push and pop, even though they shouldn't, because that's a stack, right? Yeah, let's go ahead and implement this now. All right, I'm going to come over here and new class. I'm going to call this class a queue. All right. And let's go ahead and design the interface first. Public T DQ, right? UUE, there we go. And this will return the element at the front of the queue. Removes and returns the element at the front of the queue. Right? And then the DQ operation should be a public, that's DQ. The InQ operation would be a void function that adds it to the where? Adds the given element x to the end of the queue, right? And so we need to put that in as a parameter there, right? Now, again, there's no top or bottom to stack, so which is the front of the line, right? If you want to take a reverse, mirror the image, then they swap around, as long as you're being consistent about it. That things go in one end, and then they come out the opposite end, all right? All right, once again, I'm going to use composition here, because if I put it into an extends list, or a linked list, or whatever you want, right? Then that would allow an arbitrary access, right? You can go ahead and then you can have line jumpers, right? Somebody could go to the front of the line even though there are 10 people waiting, right? So we're not going to do that. Instead, we are going to use composition. Private list of elements of type T, lying list. There we go. And here's my public queue. I need to have a constructor here to initialize it. This dot underline list is equal to, do we want to do an array list or do we want to do a linked list? That's a good question. We'll come back to it here in a second. Otherwise, let me go ahead and bring this in, import this, import, and let's spell it correctly. There we go. Let's come back to that in a second. Let's actually do the operations. Because once I've got a list, I don't need to worry about what the implementation is. Is it a linked list or an array list? No, I program towards the interface. Remember dependency inversion, right? We program towards JDBC. We don't program towards MySQL, right? We program towards an API. So what about DQ here? Well, let's do it in queue first. Maybe that's easier. This dot underline list. Where am I going to add it? To the end. So add last. Okay. If I'm adding it at the last, and then where would I remove it from? This the other end, which is going to be remove first. Now I could have swapped those out. I could have add first and then remove last. It doesn't matter, right? You're working one end and versus the other end. All right. All right. And I need to return that, I guess. Okay. All right. We still need to, of course, implement it. We need to choose an implementation here. So what about an array list? What if I were to depict this as an array inside? Right? So let's go ahead and draw that as an array. There we go. And then there are a bunch of cells here. Well, my first problem is what? What happens when this array that's in this queue gets full? We've got to expand it, right? So that comes at a cost, right? But also, what happens when I've inserted, say, 1, 2, 3, and 4, but now I need to DQ before I continue. So the next thing out of here is 1. Can I leave a gap? Nope. So what ends up happening, every time I want to DQ, I need to shift everything over. And as we've seen already, that's expensive, right? If I've got a very, very large array, right, 1 million elements, then 1 million things have to move just to remove one element, right? It can be done, and it can be done efficiently. I will show you how in a second here, but that doesn't seem like the ideal solution. What if we used a linked list instead of elements of type T? And I need to bring that in, but otherwise, all right, you can work at the front or at the back, right? Now, what does that look like here? Right, not too big. Let's go ahead and get rid of that there. All right. Now I'm doing a linked list instead. So, got that. I've got that. I've got that. And by the way, I'm keeping track of a head, and I'm keeping track of a tail, because I'm using the Java linked list. And remember that it's doubly linked, so it goes backwards and forwards. Okay. Now, if I'm going to enqueue, right, at the one end, that's just creating a new node and adding it to the tail. What about dequeue? Do I have to shift everything over anymore? Nope. All I have to do is remove one node. It's a single operation, or a collection of a few operations. It's not shifting 1 million things over, right? That is way more efficient, right? Why are you complaining? Oh, new. Forgot my new keyword there. And now I can, oh, nope. This, oh, what the hell? That's terrible generated code. There we go, that's much better. All right. Let me come over here and let me change this. I can get rid of that. Now let's go ahead and create a queue for integers. I'll call it queue. Integers is equal to new queue. There we go. Queue.enqueue 10, 20, and 30. And I'll do the same thing I did up there while the queue dot is not empty, meaning that I'm going to have to implement that as well. I will go ahead and dequeue it, queue.dequeue. And let's go ahead and system.out.print that queue. All right, so that we can see things coming out there. Now the solution here will be to create that method. What should it look like? Again, this dot underline list dot is empty. We're just going to make it a thin wrapper. That's, again, why we call it a thin wrapper. A lot of the times, if you want the functionality, it's going to be the same exact function call, but on an underlying data structure. Right? All right, let's come back over here to the demo. You know what? We can get rid of the stack. Right. Let's go ahead and, what should it come out in? 10, 20, and 30, because that's the order that we put them in. Right? Remember that it's a first in, first out data structure. By the way, what about all the other questions that we had with the stack? What happens when you try to dequeue from an empty queue? You can throw an exception. You can return a dummy value. What happens when, we can write that down, right? Other considerations, right? What happens when you dequeue from an empty queue, right? Throw exception, return dummy value, etc. Right? What happens when you enqueue into a full stack? In other words, you design that stack to have a capacity, like we did with our that queue to have a capacity, or not a stack. I mean queue. All right, there we go. But both of them, you could design it with a maximum capacity. Let's do that for a queue. What I'm going to do here is I'm going to add private int max capacity. And what I'm going to do is I'm going to want the best of both worlds. I'm going to interpret 0 here as no max capacity. Right? And so what I can do is I can have two constructors here. One that takes an integer, max capacity, and sets it. So this dot max capacity is equal to that max capacity, right? And then the other one here, we'll call that other constructor here with 0 indicating that there is no fixed capacity that you have to pay attention to. Right? Now, when we enqueue something, we have to ask, is this thing full? If this dot is full, then we either throw an exception or we do a no operation. I'll do a no operation. Right? So no op. Right? Otherwise, we return. We add this. Okay. That means that I need an is full method here as well. Is full. Now the key here is going to be checking that max capacity to see if it's non-zero. If this dot max capacity is greater than 0, and this dot underline list dot size is equal to that max capacity, this dot max capacity, then I can't put I'll return return 0 or return true. Sorry. All right. Otherwise, I'll return false. So if the max capacity is 0, remember that what that's called? It won't even bother checking this thing over here. Because it's in a conjunction and it's called short circuiting, right? This thing says, oh, that's false because the max capacity is 0, right? And so we'll immediately say, no, it's not full, right? Or we'll immediately return false in that case, excuse me, right? Now, hopefully you're still not writing code like this. If expression return true, else return false. How could I simplify this? Just return the expression. That's it. Right? You don't have to check to see if it's true. You don't, and then have an if-else-if statement here. Just simply return the expression itself. Because if the expression is true, you would have returned true anyway. If the expression is false, you would have returned false anyway. Let's see if it actually works here. I'm going to create a queue that has a maximum capacity of 2, so that when I insert 10 and 20 here, 30 will be rejected. Right? And so when I dequeue everything, I should only see 10 and 20. 30 got just thrown away. Right? 10 and 20. Right? Now if I restore this and say, oh, you can have 200 elements in your queue, then go ahead. Yeah, 10, 20, and 30. All right. So what happens when you enqueue into a full stack? Nothing. You throw an exception, etc. Right? Yep. So other variations. Right? You could support arbitrary removal or insertion of elements. Right? Actually, let me go with just removal for now. In other words, line leavers. Right? People who leave the line. This happens all the time, right? There was a lunch rush at a place, and I saw that this line was huge, and so I got in it hoping, that it would go quickly. It wasn't going quickly; it was slow. So I thought, screw this, I'm out of here. I left the line. Right? I was in the middle of the line at that point. So in other words, you would have to support the arbitrary removal of arbitrary elements. Right? But if you wanted to simulate that for whatever reason, then yeah, you could do that. You could allow the opposite. You could allow the arbitrary insertion of values, right? We call those line jumpers, right? Somebody cuts in front of the line, or there's a VIP person, right? This happens at Disney World all the time, right? If you pay enough money, you get that, what is it called? It's a fast pass or something. What is it called? You get to go to the head of the line, right? Which is just another line. It's just a smaller line of people who have paid more money, right? So VIPs or line jumpers, you could allow that. In fact, if you generalize this, you could have what's called a priority queue. A priority queue allows you to define priorities and insert elements into locations where the elements are served the highest priority first. Right? So you've got 10 people there, and 5 of them are very important people. 5 of them are very unimportant people, and then you're kind of in the middle, right? I'm not really important, but I'm not really unimportant. So where do you go in the line? Oh, you get to cut right in the middle of the line somewhere, right? You can also support multiple operations at either end, right? For queues and stacks, right? You could support a limited capacity. I think we already did that, right? But you could also support 2 operations at one end and one operation at the other, right? Now, why would you want to do that? Right? Let's visualize it, okay? So let's go ahead and redraw our queue here. Right? Now, the normal operations are that you can go in on one end, right, and then come out the other end. Right? This is the front, and this is the end. Why would you ever want to support somebody that comes into the beginning there? Right? So 2 operations at one end, only 1 operation at the other end. This is kind of the aforementioned higher priority, right? This is a line cutter. Now, in real life, that's not fair, but in computing, we don't want everything to necessarily be fair, right? What situation would we want where something gets to go to the head of the line? It has a higher priority of execution. For example, OS operations, right? If the OS can't do its stuff, then it doesn't matter what program you're running on the operating system, it's all going to grind to a halt. So OS operations could jump to the head of a scheduling queue or something, right? In fact, Unix supports this. It's called it's called niceness. Let me come over here. Which nice? Yep, there he goes. Man, nice. Right. So it'll tell you all about it. Execute a utility at an altered scheduling priority. I think that it's a value of 1 to 20, actually. By default, 10. Right? So the nice utility runs a utility, in other words, a program, at an altered scheduling priority by incrementing its nice value at the specified increment or a default value of 10. So what are the other possibilities here? Right, 5. What is the highest? 5, assuming the prior. Yeah. So the highest priority is 0, and then the lowest priority, I guess, unbounded. Right. So you can make it as low as possible. For example, not just operating system stuff, but database backups. Right. You don't. The database backup is really, really expensive. So you want to do that at night or something when there are fewer users on. But also, you would want it to have a very low priority, so that the database backup is doing its thing, but then a user comes in and tries to use the database. Oh, no, please, sir, go to the front of the line, right? You're more important than I am because I'm just a database backup, right? You can run utilities with very, very low priority, and then they'll be, they'll eventually get executed, but they'll be put off until the very end, right? When computing power becomes more available, right? And so this allows you line jumpers and priority, right? What I want to do for the other one is visualize it as a stack, right? So here's my stack, okay? No, that's not my stack. Got to have jagged edges if you want it. There we go. So we can push stuff and we can pop stuff. So push and pop. But maybe also I want a little trap door down here where I can also pop stuff at the bottom, right? Why would you want something like that? Right? You use this every day, actually, right? Kick up a word processor, type something, right? And you go, oh, okay, right. Oh, I didn't mean to delete something. I didn't mean to do that. What do? Control Z. What does that do? Undo, right? So this is an action that comes in, and then this is an undo, the action. When you undo something, you undo the last action. So if you have action 1, action 2, and action 3, and you hit undo, Control Z, you don't want that one to undo. You want the last one that you just did to undo, right? That will undo, right? But you can't store every single action in memory or in a file or something like that. So in other words, what we'll do is we'll say the last 20 actions. Now what happens when a new action comes in A4? Right? Do we want to get rid of A3? No, because that is the order that we came in. So we have a trap door down here that the oldest action gets pushed out instead. In fact, Word does support this. What we can ask. Where's my web browser here? Come on. I think it's 20 actually. Max number of undos Word. There is an undo limit, and apparently you can change it if you join the Windows Club. Come on. All right, fine. What is the default? I thought it was 20 or something like that. Maybe it's 100. Yep. If the mere number of mistakes is more than 20, you won't be able to undo things. Try it sometime. Try doing 30 actions, and then try doing undo, and you'll see that you only have a limit of 20. And it's because it's using a double-ended stack like this. Right? Although the default number is 20, you can reset. You can set almost 100 in some cases. How old is this? All right, there's no date on this, but whatever. It's a registry key kind of thing. All right. That'll take some work to get there. But apparently, is the default still 20 in 2026? Come on. You should at least up that. Anyway, you can only do it between 0 and 100. All right? So you could actually set, make it into a regular old stack here and disable the ability to undo anything. So go ahead and this weekend, if you're bored, try to see if you can find out what the default limit on your Word document is. Right? But otherwise, that's another use case there, undos. You don't want to keep them all in memory because, of course, you'd run out of memory at some point. Right? All right, to wrap this all up, let's talk about everything in practice. Don't roll your own implementations unless you have to. And for this course, you will have to. Your final assignment, you're going to be writing a sorted list implementation. But instead, you use what's built in. And in the case of Java, that's list, array list, and linked list. Right? What about stacks and queues? Stacks and queues in Java. Right? Yes, there is an implementation. It's called a deck. Right? And there's a good reason for this. This is pronounced deck. Right. It's not DQ, but that looks kind of like DQ, but it's pronounced deck. Right. Let's just go ahead and pull up the documentation for this. So come on. Nope, web browser. Java deck. There we go. Basically, they just want, there is an old school stack implementation that's still part of the Java, but I think it's an interface or whatever. But a deck is the one thing to rule them all, basically. A deck is an interface that gives you both operations at both ends. So you can treat it like a stack if you want to, or you can treat it like a queue, or you can treat it like a double-ended queue. That's why it's called a deck, by the way. It's a double-ended queue. Or you can treat it like a double-ended stack, right? How would you go about, determining what you want to call when you want to call it, right? Well, if you want to work at the head, the first element, then you would use add first, remove first, get first. If you want it to throw an exception, right? Remember, in our design, we were talking about, well, what happens when you remove from an empty stack or an empty queue, right? Do you want it to throw an exception? Then you would use one of these three methods. Do you want it to return a special value? Null, right? Then you would say offer, pull, or peek instead. If you want to work at the other end, then it's last, and it's add, remove, get, or offer, pull, peek, right? So if you want a queue, these are the methods that you should use. If you want a stack, these are the methods that you should use. It's just a thin wrapper. If you wanted to use a push, then it's just add first. Right? Of course, you could always reverse that if you really wanted to and still treat it like a queue. But this deck gives you everything that you need in one place, and that's it. Right? The implementations are an array deck. What do you think that uses? An array. Right? The other implementation is a linked list. Right? So a linked list already implements everything that you would want in a deck. Right? What would it look like over here instead of our deck? Our queue. Deck is equal to new linked list. Right. And I don't think that there's a capacity there. We'll find out here in a second. Import that. Import that. And I'm going to still call it a queue. But instead of an enqueue, what was it called again? Dot offer. Right? Offer and offer. And then I would look back at the documentation here, And what is it to remove? Oh, it's just remove first. Right? So dot remove. 10, 20, and 30. 10, 20, and 30, just like before. Right? But I'm not rolling my own anymore. I'm using a deck. And that's going to be the one that you want to use for everything. Or you want to use it for stacks. You want to use it for queues. You want to use it for double-ended stacks or queues, right? And it all depends on how you call, what methods you call, right? Oh, I should mention that, wait, we said that we didn't want a queue. Oh, we didn't want to, oops, that's not what I want. There we go. We didn't want to use an array for a queue because we'd have to shift things over, right? Let's go back to that problem from before. If I'm going to treat my queue as an array inside, then that means if I have 10 here and I want to dequeue it, or what was it, remove, whatever it was called, right? That means that I need to necessarily shift things over, right? You don't have to. Here's the trick. Here's your array. You keep track of front as an index, and then you also keep track of end as an index. Now, what happens when you dequeue something? What do you do? Oh, here's 10, and here's 20, and here's 30, dot, 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 right? What happens when you dequeue something? Of course, you copy it and you return it, but what do you do with your reference right here? Just move it over. Right? What happens when you insert something? Here's 90, and we want to insert 10 here, 100, right? Then what do we do with that end reference? We move it over here. What happens when you've gotten to the end? You just wrap around to the beginning, right? Now, if it's ever full, then yes, you need to expand it, copy things over, maybe reset how everything works. But all you need to do is make sure that these get wrapped around, right? And by the way, how do you determine if it's full? If the end is pointing at the beginning, right? So that's a way that you can do it. It's kind of clever, but at the end of the day, why not just use a linked list, right? The linked list does everything without having to bend over backwards to do it efficiently like this, right? Let's see. Yeah, that's it. Any questions on lists, list-based data structures, stacks, queues? There's also a built-in, I should mention that there's a built-in priority queue in Java, priority queue. Isn't it? Is it priority queue? X. Or what is it called? Import, yep, there we go, there it is. And so I'll call this PQ is equal to new priority queue. There we go. And let's just do it for integers. Right, there we go. Now, the implementation here is neither a linked list nor is it an array-based list. It's something else called a heap. That's something that we're going to look at towards the end of the semester here. But let me show you the power of it. PQ dot add, right? 10. Let's go with 30, 20, 50. Let's go with 5 and 100 at the end, right? So what order are they in? System.out.println PQ. Let's find out what order it prints them out in. Ooh, the order that I kind of put them in. But let's start taking things out. PQ dot, what is it, remove? There we go. While PQ dot is not empty, let's go ahead and remove an element. What's going to be removed first? The thing with the highest priority. These are integers, so what's going to have the highest priority? It's the natural ordering. 5 gets removed for, oh, I should print them out, sorry. System.out.println PQ.remove. All right. So what's the very first thing that's going to come out? 5, 10, 20, 30, 50, 100. What order is that? It's been sorted, right? So at the end of the semester, the very last thing that we're going to look at are heaps and priority queues, because it exemplifies what we started in the very beginning of the semester. One of the themes of this course is that smart data structures and dumb code are a lot better than the other way around. With a priority queue, you can put stuff in and then take stuff out. It doesn't get any dumber than that. Dumb code. Put stuff in, take stuff out. But what has magically happened? It's been sorted, right? It's called heap sort, right? Smart data structures and dumb code are a lot better than the other way around. This is smart data structure right here. Dumb code, put stuff in, take stuff out. In contrast, think about, say, quick sort. Really, really clever code. It's recursive, right? It can be done in place. You can fine-tune your pivot choice, et cetera, right? Clever code, no data structure, right? This is a lot better than the other way around, right? Okay. Any questions? Well, what are we doing next? Oh yeah, next thing we're going to be doing is algorithms and algorithm analysis. Have you done that in 235 yet? You get what? You're getting there? All right, so like, have you done big O, big theta, big omega? Okay, all right. Then that's what we'll be doing next, right? But we'll be doing it from the practical standpoint. For example, just to motivate it for next time, let me go ahead and write a really quick public static void, actually no, int sum, a list of integers, numbers. All right, for int I equals 0, I is less than n, or numbers dot size, I plus plus. Right? This is code that every single CS person would write. Right? Total plus equals numbers dot get the ith element, and then return the total. This is correct code. Is this good code? All right, take the weekend. I guess you could call it a trick question. This is terrible code, right? And to understand why, I'm going to give you a demonstration on Monday of why this is terrible code. As a hint, have we ever talked about the painter before? The guy painting a fence? Okay, I thought we had. Do you remember?
Sounds familiar.
Sounds familiar. So the guy pays this guy to paint his fence, and he says, "I'll pay you $1 an hour. I'll pay you $1 an hour. You only have to pay me $1 an hour, right?" And so, the first hour he gets a lot of the fence done, right? So he's really happy. This is going to be really cheap, right? And then the second hour he's only got a little bit more of it done, right? He goes, well, maybe he took a break or something. Comes back the next hour, he has even less of it done, right? Less. And he says, well, what the hell are you doing, right? What am I paying you to do here? Show me how you're painting the fence. So he says, all right. He starts at one end, puts his paintbrush into the paint, walks all the way over to where he's painting the fence, continues, runs out of paint, walks all the way back to the beginning of the fence, dips his paintbrush again, and does that over and over and over again. In the very beginning, when he's only painting a little wide area, he's only walking a little bit. But now as he gets to the end of the fence, what is he having to do? Walk back and forth. This is terrible code because it's walking back and forth, right? We're going to see why on Monday. All right, just remember the painting guy. All right, see you on Monday then.